Welcome to this video. My name is Wycliffe, and in this session, I want to share with you how you can calculate or monitor vapor pressure deficit over your plant. Now, this is the difference between pressure of vapor in the air and normally pressure of vapor in the plant. So if we have very high vapor pressure deficit, then it means the difference between moisture in the air and moisture in the plant or vapor in the plant is the gradient is high. So that will then force plants to lose more water because water will travel from high concentration region to low concentration region, especially if it's on a windy day. So let's see how we can calculate that simply for our region of interest using Google Earth Engine. Okay, so let's get started in RStudio. So I already prepared this for you so that we don't take too much time typing all this. So we will start by getting bounding box for Kericho, which is a region in our from global administrative layers. We can extract that feature. Then we get TerraClimate, which has a vapor pressure deficit band. Then we aggregate annually and convert to multi-band, reduce our region of interest, and then create some interactive maps. Of course, if you like this, subscribe and share, and then other friends can also learn from it. Okay, but if you are new to RGE, I have added some information in the README page of my GitHub repository. So if you go there, you can find how to install and set up your RGE. So to begin with, we'll have these libraries loaded. So that is RGE, dplyr, tidyr, ggplot, and SF. Then you initialize your Google Earth Engine account. Okay, so after initializing your Google Earth Engine account, we can load the global administrative layers using feature collection. And this is the image ID which we obtained from Google Earth Engine, right? So if you go to Google Earth Engine and type global administrative layers, we have the country boundaries, but we also have the second level. This is the one we use for this case, all right? So we also need, we can filter our region of interest from this using filter and then EE filter equal to, and then we pick the property or the column which has the names for this level 2 features. Then we get Kericho for that, okay? If you want, you can check the information, you can print the size, but that's quite optional, okay? Then we load the vapor pressure deficit data, which comes from Idaho, EPSCoR, TerraClimate. So that's an image collection, which we also have in Google Earth Engine. So if you just type TerraClimate, you should see it here. And then among the bands, it has got vapor pressure deficit band, which we are going to be interested in today. And we know it's at a scale of 0.1, but the resolution of the image is about 5 kilometers. All right, so we load that. We also loaded Kericho. Okay, I hope that ran without any problem. No, there is a problem, Gaul. So we have to run Gaul first and then we load Kericho. Okay, we extract Kericho from it, then we load the global the image collection. So because we want our analysis as long as possible, if we check the TerraClimate data, it's available from 1958. So we'll set our start date to 1958. Okay, I've just changed that. So up to 2025. And sorry, we can even set it to 2024, December 31st, right? Okay. And then after that, we can create a collection by picking our vapor pressure deficit collection, the image collection, and then we filter by start date and end date. Then we select the vapor pressure deficit column of interest, all right? Then the next thing is to create a list of years. So we want to do this from 1958 to 2024. So I changed this to 1958, which we had here, and then 2024. So we create a sequence of years there. Now, if you look at years, it is just a list. But then from that list, if you want to see the actual numbers in it, then you can use getinfo, and then you will see 1958 to 2024. Okay, so after that, we can map a function, and we will map a function over the list of years, 1958 to 2024, and the function is from util_spy function. And for that, we provide a function which picks a year, then converts that year to a number, and then we get the start date. For the start date, we take that year, say 1958, January 1st, and then the end year will still be that 1958, but increased by 1. So we advance by 1 the year. The start date, 1958, which we had here, we advance it by 1 in the year attribute. And then we can create an image collection or annual image by filtering for start date and end date, the start and end, for example, January to December of this year, and then we get the mean of all those images. We can then rename this image and we format the year to all numbers so that we don't have decimal problems. Okay, then we can set the annual, the year attribute to the images, to each image. So each of the images returned here will have year as an attribute. Okay, but this, because we are mapping over a list, we will get a list of images. So we can use image collection from images function to convert them from that list of images to an image collection, okay? Then we can convert that image collection to bands by using toBands function. But remember I said we have to convert it to kilopascals by multiplying it by 0.01 because they are multiplied by 100 in the backend, okay? So we need to divide it by 100 or multiply by 0.01 to get them in kilopascals, okay? But these bands will have some names that are not, these bands, because of this toBands function, they will have some indices like 0, 1, or something like that. Let me print some. So we can have VPD bands and then $, and then band names. It's an Earth-Engine list, and then we call for get info. Then you see these numbers, yeah? These numbers are assigned when you use toBands function, so in Earth-Engine. So we need to remove them. So we keep those old names, and then we map a function over those names, which deletes that the trailing zeros, okay? So, or numbers. So we use old names and we map a utils function from Python, which takes each number, and then for that each number, we replace any digits with underscore that appears before we get to VPD. Numbers followed by an underscore. We remove all those, and then we replace them with nothing, okay? Object old names not found, so we did not run that, and run that. Then for the bands which are clean, we can rename them with the clean names. Simple. So we run that, and we have renamed our bands with the clean names. So these names don't have these numbers like 0, 1, 2, 64, 46, and all that, but they only have VPD mean 2025. You can confirm that with checking at VPD bands clean, and then get band names, and then, band names, then we get information, get info, okay? So that will print the clean names without the trailing 0, 1, 2, 3, 4 up to 70 or 66, okay? Then after getting the clean names, we may get statistics from our data, and we now use the clean bands. We reduce regions with the reducer of mean. So we use Earth-Engine reducer mean to reduce over our region of interest, which is the collection for Kericho. And now remember the scale here is the scale for the spatial resolution, not the pixel values, okay? It's different from this scale we used up here. Okay, so if we run this, we will get the statistics, and this stats is an Earth-Engine collection because we are using feature collection to run that, okay? We need to convert it to stats using EESSF, which is one of the best packages I know of. In this collection or in this package of Earth-Engine, because in R we cannot apply dplyr and so forth functions on Earth Engine or feature collection directly. We need to convert it to SF and even to a data frame, right? So after converting that to a simple feature, if you run this, you will find that it's a simple feature collection with all the columns, including even the columns of the feature collection we used to reduce. We used in the reduction here. Okay, so the next thing we can do is to take that simple features and drop its geometries so that we remain with a simple or a regular data frame. And then we only select the variables that have VPD. All these other status, admin code, we don't want them. Okay, so we run that. After that, we can then, what do we have? We should look at it. Stats.df. If you look at stats.df, we have the names of the columns that contain the actual vapor pressure deficit values in kilopascal. So we can pick those columns using grep base R function, and then all the names from that df, and we return their values. So this is just a list of names or a vector of names of the columns we have in stats.df. So that can help us to do cleaning of the data. So we will select all of them, and then we pivot longer where columns take everything we have here, and then names go to maybe band. We can specify anything here and values to a vapor pressure deficit. So if we run this alone, you can see that the data has now been converted from the wide format we had up here to a long format where we have band and vapor pressure deficit for specific years, okay? Then we go ahead and mutate a year, which therefore cleans all values that appear before the 4-digit number, before the 4-digit year number. And then we replace them, we remove them and only remain with the year, okay? Then we can arrange by that year. So if we run that and we check our DF, it is now having a year, which is an integer because we specified to convert it to integer other than character, and then with the vapor pressure deficit. Okay, so we can plot this, our DF, because we now have two columns of interest, vapor pressure and the year. So those forms our X and Y axis, and then we use geomline and geompoint to join the line, like to have them at the intersection of the axis, and then we set the minimal and we provide the year, the title, and X and Y axis values. So that gives us this nice plot. Okay, from this plot, we notice that the year 2007, because this is 2000, and therefore this is 1, 2, 3, 4, 5, 6, 7, and 2019, because this is 2020, and the preceding one is 2019. So those 2 years have very different values. Again, you can also see that over time, the water vapor pressure deficit is increasing, meaning the air is becoming drier and drier in this region. We have not done any statistical assessment to check this, but you can see there is some random variabilities over time, and especially after the year 2000. Before the year 2000, it was rather stable, though increasing, but not so much. The variability increased after the year 2000, okay? That can be detrimental to the plant, especially when we have high deficit. So the vapor pressure deficit is high, therefore the water must leave the leaf of a plant through the stomata, and the plant may suffer if a lot of water is lost from the leaf, okay? So we have seen that, and we've marked the 2 years, so we can visualize the 2 years with just, first of all, we center our map to our region of interest, and then we can add layer for the year 2007 and the year 2019. Using this arrow bar, we can look at them side by side. So we run that, and then that runs well, and then we can see in the viewer, we should have a comparative image where we can see on our right, on this right-hand side, we have for 2019, and on this left, we have for 2007. So you can see in 2007, most parts were green, but in 2019, we have more red because there we have high deficit of water, right, in the plant. So the plant suffered more. in 2017, in 2019, right? Let me check. Yeah, 2019 than in 2007. You can use this to inform some yield, if there were some yield patterns that were abnormal or other things were good, but if the deficit of water in the air was high, then the plant suffered more in balancing the water or water balancing between the plant and the atmosphere. All right. So that's all. This video, this script, I will put it in the description, a link to it, to my GitHub repository where you can get it and try it for your region of interest. This kind of analysis is probably optimal for larger regions because here you can see actually individual pixels. You can actually see the individual pixels, which may not be the best thing. So you can apply it in a larger region, but if the scale of 5 kilometers is fine with you, then that's applicable for your case. So that comes to the end of this. If you enjoyed this video, like it, share it with colleagues who would wish to learn this, and happy coding. Bye-bye.